Bismillahirrahmanirrahim. Today we will discuss UV visible spectroscopy. First of all, what is spectroscopy? Spectroscopy is the study of spectrum. Now, spectrum is the band of energies that is produced by the interaction of matter and energy. When the interaction of the energy occurs with the matter, there is transition of electron. Due to this transition of electrons, spectrum is formed. Now, what is transition? Transition is the transfer of excitation of electrons from one energy level to the other energy level. So, what is spectroscopy? Spectroscopy is the study of interaction of the electromagnetic radiation with the matter, and as a result of this interaction there is transition of electrons, and the transition of electron is actually the shifting of electron or the excitation of electron from ground state energy level to a higher state energy level. Coming towards the topic, what is UV visible spectroscopy? UV visible spectroscopy is the special type of spectroscopy in which only we study the interaction of UV visible radiations with the matter. Now, UV visible radiations uh, ranges from their wavelength ranges from 200 nanometer to 800 nanometer, out of which UV ultraviolet radiations ranges from 200 to 400 nanometer, and the visible radiations ranges from 400 to 800 nanometer. And the for UV spectroscopy is studied under vacuum, and the common solvent used for used for analysis and study of interaction of the ultraviolet and visible radiations uh, is hexane or ethyl alcohol. Hexane and ethyl alcohol are used for the study and analysis of interaction of UV visible radiations with that solvent. Now, what is actually the electromagnetic radiation? Electromagnetic radiations are actually the photons that are traveling in the form of wave. They have dual nature. They have nature of energy, as nature of matter, as well as uh, the abilities of a wave. So these are the electric and magnetic fields traveling perpendicular to each other. This is termed as wave particle duality, possessing both wave like and particle like characteristics. Now we will discuss little bit about the spectrum. As we know that spectrum is the band of energies, or we may say that spectrum is the band of wavelengths. And this spectrum, starting from the gamma rays and ending at the radio waves, uh, if we move from the uh, left side to the right side, there is an increase in wavelength, and hence but there is decrease in the energy. With the increase in wavelength there is a decrease in energy, hence shorter the wavelength, the maximum is the energy. So the energy is maximum at the start of the spectrum, and energy is minimum at the end of the spectrum, and wavelength changes uh, opposite to the energy along the spectrum. So when the interaction occurs between the electromagnetic radiation and matter, what occurs? We know that at room temperature the molecules are at their lowest energy levels, also termed as ground state energy levels. When these are focused, these are exposed to UV visible radiations. The electrons are promoted to higher energy level, and these are called electronic transitions. Depending upon the energy of the radiation falling on the matter or the solvent, the the transitions may be electronic, vibrational, and rotational. The X rays, the radiations with minimum with lowest here in this picture, with the lowest wavelength, have the maximum energy, and they causes bond breaking. And then next are the ultraviolet radiations that have a little bit lower energy, and these cause electronic transitions, mean shifting of electrons from one energy level to another energy level. And then next we have vibrational transitions, in which electrons vibrate, and just there is shifting of electron between the vibrational energy levels. These in these levels, energy level, there is a little space rather than the electronic energy levels, and it may be from 0.01 to 1 kilocalories per mole. And in rotational energy levels, there is the minimum space, and these are discrete and quantized energy levels. So in one electronic energy level, there are several vibrational energy levels, and in one vibrational energy level, there are several rotational energy levels, and hence uh, we can see here that the energy difference between these transitions changes, that there is minimum energy difference in rotational transitions, and then in vibrational transition, and the highest energy difference is in electronic transitions. Now we have Beer-lambert law that describe the absorption of these radiations by the matter or the solvent. It states that when beam of monochromatic light passes from a substance, the absorption of light is directly proportional to the path length and is directly proportional to the molar concentration of the absorbing substance. So with the increase in the path length, that if the beaker possessing the solvent is increased in width, then there the light covers a greater distance from the solvent. So with the increase in uh, path length is the distance that light covers inside that solvent. With increase in path length, there is an increase in absorption, and if we put more solute to that solution, and there is an increase in concentration of the absorbing substance. So with the increase in absorbing substance, according to Beer-lambert law, there is an increase in absorption. Here we have the relation for Beer-lambert law, uh, in which I naught is the intensity of incident light, I is the intensity of transmitted light, and that is equal to intensity. This is intensity, and next C is showing the concentration of, and L is showing the path length that the light covers inside that absorbing solvent. Now we will discuss these transitions in detail, that when the energy falls, electromagnetic radiations fall on a molecule, fall on a compound, then there is shifting of electrons between the energy levels. Now what are these energy levels? Now we can see here that these S uh, and P are the bonding energy levels, and this N is showing the non-bonding energy levels, and these are anti-bonding energy levels, and S star is the anti-bonding energy level to the S, and P star is the anti-bonding energy level to the P. we from this arrow is showing that the lowest energy level, the lowest orbital has the minimum energy, and as we move towards height, there is an increase in energy level. So when electrons shift from the s orbital to the s star orbital, there is the maximum energy difference between mm, in this transition. And so this shows that the minimum bonding in the orbital with minimum bonding energy has the anti-bonding orbital with the maximum energy. The orbital with minimum bonding energy have the maximum anti-bonding energy orbital, that s has the minimum energy, then S star would have the maximum energy, and P has a little bit more energy than the s orbital. Then its anti-bonding orbital would have uh, a little bit minimum energy than the anti-bonding orbital of the s. S to S not S to S star shows the sigma transitions, and these bond are formed in the alkanes. These are present in the molecules with single bond, and then S to P transition occurs in the molecules with double bond like carbonyls. P to P star transitions occur in unsaturated compounds in like alkenes and other unsaturated, and N to S naught transitions mean non-bonding to S is the sigma star. These occurs in the molecules with the possessing the lone pairs of the electrons, and N to P star occurs in the carbonyls. Now, actually, what are these bonding, anti-bonding, and non-bonding molecular orbitals? Actually, the non-bonding molecular orbitals. Actually, the bonding molecular orbitals are the orbitals that in these the stability of the molecule is decreased in the presence. When a molecule is formed from the atoms and there is formation of the bonding molecular orbital, the molecule form would be more stable. Mean there would be a decrease in energy of the electrons in these molecular orbitals rather than when they were present in their atomic orbitals. And in case of anti-bonding molecular orbitals, there is an increase in energy, and hence the stability of the molecule is decreased. uh, in case of non-bonding molecular orbital, when these are formed, there is no change in the energy of electrons, so these do not affect the stability of molecule. Let us describe these transitions one by one. That is sigma to sigma star transition, when a an a electron in a bonding s orbital is excited to corresponding anti-orbital, that is s star, or from sigma to sigma star. The energy required is a maximum. In case of this transition, there is maximum energy difference, as there is absorption of the the wavelength of 125. It means that this wavelength of 120 to 125 nanometer would have the greater amount of energy, because energy and wavelength are inversely proportional to each other. In case of n to sigma star and pi to sigma n to pi star and pi to pi star transitions, there is a little bit decrease in energy. I mean, with when the radiations of a little bit lower energy level are absorbed, then these transitions occur. Actually, these transitions uh, are very they have a concise rule that suppose the two orbitals have a particular and fixed energy difference. So the photons with energy equal to this energy difference will only be absorbed. If the photons have energy a little bit lower than this energy difference between two energy levels, or higher energy, if the photons possess higher energy than the energy difference between two energy levels, then no transition will occur. Only transition will occur when the energy difference or energy gap, uh, if the energy possessed by photon is equal to the energy gap between two energy levels. Then next we have n to sigma star transition, when the when a lone pair, a non-bonding electron, uh, jumps to the sigma star transition. Actually, the anti-bonding orbitals are not occupied at uh, at room temperature. These are only occupied at the when the energy is provided to the electrons, and these actually cause the breaking of bond, because there is too much increase in energy, and the increase in energy decrease the stability of the molecule, and hence they cause uh, breaking of the bond. These electronic transition that are sigma to pi star and pi to sigma star are forbidden transition, and they are only theoretically possible. They are not practically possible. In organic molecules, the UV visible radiations are only absorbed by the functional groups carrying multiple bonds, and these are called chromophores, capable of showing uh, that are capable of absorbing UV visible radiations, and hence showing transitions of the electrons, and in the result of transition of electron there is formation of the spectrum, rather than the other molecules that have difference energy, uh, and they cannot absorb, hence they cannot absorb the UV visible radiations, and they are unable to show the spectrum. Next we have so the multiple bonds carrying functional groups that are capable of absorbing UV visible radiations are chromophores, and exochromes are the functional groups that are attached to the chromophores, and they increase their ability to absorb the UV visible radiations. They are helpful in their abilities of uh, absorption of the UV visible radiations. Next, we have the relation between absorption and intensity shifts. First of all, we have bathochromic shift, in which when the maximum of compound shifts to the longer wavelength, then this is called bathochromic shift. What does it mean? It means that the when we change the concentration of the solvent, then it starts absorbing the radiations of higher wavelength, and this is called the absorption of higher wavelength is called bathochromic shift, and it is also called as red shift. In opposite to the bathochromic shift, we have hypsochromic shift, that is when the maxima shifts to the shorter wavelength, that when we change the concentration of the solvent starts absorbing the radiations with the shorter wavelength, and this is called hypsochromic shift. In here we have the hyperchromic shift and hypochromic shift. When the absorption intensity of the compound is increased, mean intensity increased, mean the absorption is increased. Absorption intensity mean that there is an increase in the absorption of the light, like we said that when we add the exochromes to the um, uh, to chromophores, then this starts absorbing the higher there is an increase in absorption. So when there is an increase in um, absorption, it is known as hyperchromic shift, and if the intensity of absorption is decreased, mean that absorption of the light is decreased, then this is called hypochromic shift. Here we have some applications of UV visible spectroscopy. That one is qualitative and quantitative analysis. It is used for characterizing uh, aromatic compounds and conjugated olefins It can be used to find out molar concentration of the solute under study. And then there is detection of impurities. We can detect the impurities in the solvent. It is one of the important methods to detect impurities in the organic solvents. Detection of isomers are possible, and determination of the molecular weight using Beer's law. That was all about the UV visible spectroscopy. Thank you for watching the video.